Thank you. I will just start my presentation. Yeah, so first of all, thank you for the invitation, and thank you to the audience for dialing and listening in. A bit about the program for today. So I will give a short introduction about myself, my background, and then I will explain some use cases at CLAAS where we employ AI, and a bit about the history behind these use cases and why AI has been the tool of choice. I will talk a bit about the building blocks that we have internally in order to facilitate new development in AI, and some of the challenges met when working with AI. Mostly practical challenges, some were already mentioned in previous presentations, and then in the end some of the conclusions we've made so far. All right, so my name is Allan Kildeby. I'm 53, married, 2 daughters. I have a background in computer vision, master's degree from 2002, and I've had the luck of following the transition from what we call classical computer vision into AI-based computer vision firsthand, from the earliest steps until where we are today. And maybe a short note on computer vision. There are typically 2 different types of techniques that we employ. One is classical. That means by writing an algorithm where I, as a human, evaluate what is the right approach to find specific features in an image. And the other way of doing it is by using AI, training a model on data that you have captured over time, and then have the model identify the parameters and characteristics of the features that you are looking for. In camera sensors, I like this diagram of where we are. So we develop, much as Garford, we develop the complete solution. In this case, we develop camera sensors, which means we are responsible for the algorithm as well as the optics and sensors. And having all these 3 disciplines at hand helps us to position ourselves in a sweet spot where we can accommodate the best possible solution for the problem at hand. All right, the first use case I will look into is evaluating silage quality in forage harvesters. So currently, there's no, or until recently, there was no means to evaluate the quality of the product you're chopping online. You would make a physical sample, send it to a laboratory, wait days, and then you would have a result days or weeks after the harvest has been completed. Additionally, it would be spot samples when you're harvesting 200 or 300 tons an hour, and you can make a 1 to 2 kilogram sample and send it to the laboratory. It's not really descriptive of the complete product. The farmer typically either over or under processes using static settings. So you set the machine, you drive through the field. In some cases, you adjust it meanwhile or during operations, but you have a limited means of evaluating the result, and the output of that is either lowered digestibility, or you will waste fuel in over processing. The changes in the field also happen rapidly, which means that you need to monitor it continuously, real time, and have a robust way of doing that. The target, according to the CSPS procedure, a method that was suggested by David Mertens, I think in the early 2000s, is that if you filter a physical sample, then more than 70% of the starch, so mainly kernels, shall fall through a sieving grid with a size of, I think it's 4.75 millimeters. And more than 70% means optimal yield. I've shown a diagram below that shows a typical distribution of the CSPS across several hundreds or thousands of samples. It varies from year to year, also depending on sampling laboratory. But in general, the process is standardized and the same. And how did we then approach this? Well, I can say this is probably one of the more lengthy approaches that we've had to a computer vision problem. A lot of different methods and parameters have been investigated. Everything from structured light, multimodal imaging, NIR, different sample sizes, change of frame rates, but most of them based on classical computer vision means, which has its limitations and not made us capable of solving the problem. In 2018, we started a PhD project, which was later then continued in a second PhD project. And during these two PhD projects, we established proof that evaluating the kernel fragmentation and estimating a CSPS score, which means corn silage processing score, online using visual means and an AI model trained to do so, actually correlates very well with machine settings. And what you in the end need to do, one of the primary parameters that affect the chopping quality is the cracker gap distance, so the part of the forage harvester that processes all the kernels. It uses, of course, a lot more power if you are having it on the minimum distance all the time, then you press all your material through a very narrow gap. And the other way around, if you open it completely, it will probably not process enough, and you want to be able to adjust this online, and that is what we have achieved. So as a spin-off or a necessity, the need for a high-speed cracker gap adjustment was identified and has also been implemented. And this product has been presented or will be presented at Agritechnica, and has also been awarded a Silver Innovation Award medal alongside two very similar systems, one from New Holland, CNH, and one from Fendt Akko. And I feel confident that Morten Bilde will maybe say a few words about that in his presentation. Yeah. But the system in general works in the way that you have a camera mounted in the spout. It monitors the material that goes through at a high frame rate, evaluates the CSPS, which then feeds into an automation system that automatically, among others, adjusts the cracker gap, and then the loop reiterates, and you capture new images and evaluate the change. And this is done more than 20 times a second to achieve the adequate responsiveness. Another use case where we where we started out more or less only using classical computer means and with quite a success is a similar system in a combine harvester. Here the target is to evaluate the quality of the crop that flows through the combine harvester. And here the challenge was somewhat different. We had a system that works fairly well in a number of crops. However, there's a desire to extend the amount of crops or fruits supported. And one of the drawbacks of the technology used so far is that it relies on classical computer vision. And the more different crop types are, the more specific algorithms you need to write to both the crop at hand, but also the different types of impurities. So the magnitude of the number of specific algorithms you need increased drastically. So there's a desire to find a different approach where you could reuse some of the components from other fruit types. And of course, there's a trade-off also using classical computer vision means. Classical typically aims at finding a general description of an entity, and the more your specimen diverts from this, let's call it general description, the worse the algorithm works. So you can have fields where it works less than optimal and others where it works optimally, depending on the variation of the crop and field conditions. So here again, AI was the tool of choice. And one of the things that we achieved with AI is to drastically increase the frame rate. I think the existing or old system ran at around 5 frames per second, and with AI we are able to achieve more than 25 frames per second. And this, of course, allows a lot more frequent sampling and a more reliable result. As a, let's say, a bit maybe in contradiction to what was said earlier, we are actually able to reuse some of the components. So a model that works well for one variant of wheat may work similarly well for another variant of wheat, of course with the adequate or the right data, but the model as such can be reused at least for similar grain types. So you can imagine using one architecture for wheat and for rye and for barley to at least cover most of the features you're looking for. One of the findings we did in this project was that the annotation quality, so the manual markings or the markings you make in the sample data in order to train the model, of course, has a very large effect on the quality of the product, but it is also more difficult in some situations than others. So the need for cross-validation was apparent, where you have a number of annotators annotating images, and if you have discrepancies between what one annotator thinks is a broken kernel and the other doesn't, then you will have an expert evaluate the result and decide. What we also found out with the AI was the ability, or what we achieved was the ability to find broken kernels where the typical features are not visible, meaning in the optimal case, you see a white broken surface of a wheat kernel, but even if the kernel is laying on its side and you can only see the cutoff side of the face, then you will still be able to detect most of these instances. And here it's a similar loop to the system just described. You capture images, you detect the features, then you feed this into an automation system that optimizes a number of system parameters for threshing and cleaning. And then you actuate or move your actuators, and again, the feedback loop starts. The last use case I will describe is avoiding rumex wheat in grasslands. Rumex is a let's say dominant weed that in this case pushes away grass in grasslands. It reduces fodder quality by competing for light and nutrient and space. And if the amount of rumex is excessive, then it can lead to illness in the cattle that is feeding on this material. It's typically something that you would address either mechanically or by with pesticides, but since blanket spraying is not a viable option, you want to dedicate, or you want to approach or target it specifically in the locations where it is found. And this means an approach where mapping of the instances is a desired outcome of that for later processing. So in this case, it has been, let's say, a new greenfield development. So in this case, we didn't have a system that can do this right away. We have some systems that operate similarly. We have a competing system to what's described for Garford, and some of these experiences here could be reused, but the model as such was newly developed to solve this specific use case. And we use a deep learning model to train on data annotated from a number of different cameras. And then we geolocate these by combining it with GPS locations. And this is then mapped into a map that's accumulated over time. And once this map is completed, it will be transferred to a backend system for later use or for later deployment on another target platform. This could, for instance, be a band or spot spraying system. The benefit of this system is, of course, that once the farmer is going out to apply pesticides, he will know how much to bring, meaning that he will not drive around with a full tank, impacting soil, and also spending more fuel than necessary. So it has a potential to be to save cost for the farmer. Yes, I think that's about what I wanted to say about this. Yeah, maybe a side note. The model was initially developed completely offline by cameras mounted on a manual fixture and in a different department than ours. And we were then contacted in order to integrate this model. And this just shows that the topic of AI, and specifically in visual applications, is also spreading out in the organization and being rooted mostly in advanced development departments, but also in other departments. Some of the building blocks that we have available to create these systems we have let's say an embedded platform that we employ in all our camera products. This platform offers a hardware accelerator or an NPU that can execute these AI models. It will handle 1 to 3 camera sensors or image sensors, and you can configure it in several different ways depending on the use case. The processing platform is also used in other products, even non-camera products, simply for its NPU capabilities. So that's the main, I would say, building block for employing this. This also means that we can deploy new solutions fairly easily and quickly and test stuff out with existing products, assuming that this platform can be used for new products as well. Some of the infrastructure tool or building blocks that we have automated data pipelines, meaning that when we record in the field, we can upload these data. It'll be anonymized automatically if that's applicable for the data in question. We have cloud and local-based training pipelines. So depending on the use case and the demand for computing power, you can either do it on your you can do it locally or in the cloud. We employ quantization-aware training as well, depending on what target device it's to be deployed on. That means if it's a target that has limited hardware capabilities, you may want to convert your model to dealing with integer numbers rather than floating point, and this is what we call quantization-aware training. We have a number of different tools employed for this. Most of them are, let's say, new and driven mostly by the need for AI. And we have a set of standard models and model libraries and toolkits that can be used for new use cases to get a quick head start. Some of the challenges experienced, I would say one of the major challenges, and that has been mentioned, I think, in every presentation so far, is the acquisition of data. You need to be able to cover botanical variants, environmental variants, and if that is not enough, you can either augment your data, meaning you can take the data at hand and then modify it slightly to create different lightings or color distributions, flipping, rotating, so augmenting. And you can combine it with synthetic data as well. So up here in the right-hand corner, I have an image of maize data where the left-hand side is actual real data, and the right-hand side is synthetically generated data. And that is also useful to close some of the data gaps that you will experience when dealing with AI. Data is, as mentioned again, the most important part of working with AI. We have some challenges also. We have identified some challenges in annotation and specifically annotation quality, as mentioned in some use cases, it's different for the naked eye to see the difference, and here you need expert knowledge. So depending on the use case, we employ different workflows when doing annotations. In the simplest case, where you are to annotate a geometric shape or the corners of a, I don't know, vehicle, that can be done by most persons. But if you are to distinguish two different types of impurities in a grain stream, you will need an expert. And then it has also changed the way of working. My experience is that we have started out developing algorithms a lot earlier in the past, meaning with less data, we would just go ahead and start out with something. Whereas when you work with AI, you need the data beforehand, because training data on, let's say, a fraction of the data set will not, we know already, it will not yield the desired performance. So data acquisition, data exploration, definition of data sets and so forth is really critical, and requires much more time than most expect. Additionally, new laws are governing how we are to work with AI. We have to document certain things. We have to create what is called a model card, where you describe how the model was developed, with what data, and what order, and what steps. And these requirements also influence the way we work. And as a side note, we have also had to consider new ways of releasing software and releasing updates, because a model is typically or often independent from the software application, which means that with the same software application, you can update the model a number of times, and this needs to be maintained or versioned correctly. And yeah, maybe on a side note, that the model you develop is will not be better than the data you have and the annotation you feed into it. So I can only emphasize that data is the key to success here. Yeah, so this will mostly be a repetition, I guess, of things that I've said so far, but in general, what we have concluded is that AI has represented a steep learning curve, and has led to a transformation in both technology and the way we work. It unlocks a significant potential in especially computer vision applications for automation and autonomy. It will change, as mentioned, the way we work. It will also accelerate development cycles. Again, once the relevant data is accessible, but once the data is there, it's a lot faster to test out new models and new architectures to prove or disprove a case. It has led to the reopening of projects that were previously considered too complex to solve, at least with the technology at hand. And it does optimize, or it does offer optimization potential and cost saving for the end customer. Yeah, and with that being said, my presentation is done.
Thanks so much, Allan. Lots of rounds of applause for you there. Really exciting technology. You talked a lot about support for the user there, and just wondering, does this technology keep learning? You talk about software updates. Does it continually learn? And also, how can it be integrated into existing CLAAS diagnostic systems as well?
Well, keep learning is, I mean, in the first solutions that have been made available to the market, it doesn't learn new stuff automatically. So we can capture data in the background. I would say the biggest challenge is always getting the data out of the system. So here there's a need for further development of I would say machine infrastructure in order to supply this data. So no, currently the systems when operating in the field do not learn from what they see, but they supply data, and the models are continuously retrained with new data. Once we see a deficiency somewhere, we add data for this and retrain the model, and this can be deployed through diagnostics in this case. And the data can also be downloaded using diagnostics.
Excellent. And in terms of looking at return on investment, at what scale does this technology become cost effective for the user?
That's hard. I don't think I can answer that question. Cost effective, I would say there are some initial startup costs. I mean, you need the infrastructure to handle these projects. You can, in some cases, you could do it on a single PC if it's for a single use case with a limited application. But if you want to, let's say, start it in scale for a company of a certain size, it will incur some startup costs. My gut feeling is it's not, once you have that, it's not more expensive, probably less expensive for the end customer to develop a solution that will do the same or improve a current solution using AI as opposed to classical computer vision means.